Welcome to all in online class. Hello, boys. Um, we are just preparing ourselves for our in-house exams or pre-test exams or test exams or finally for our board exams. So we have to practice the same things or same terms again and again. We have to review the whole syllabus again. Sometimes it becomes monotonous, it becomes annoying for us, it becomes annoying to you to repeat the same things again and again. But remember one thing: whenever you are repeating the same things for several times, you just make some easier point, or you just feel easy with some topics that was quite difficult for you in earlier. And whenever you just repeat the same mathematical type questions, then you just get some more easier method to solve the question. So please don't be sad, don't be disappointed that I have to do the same things again and again. You are utilizing your time. That means you are investing your time for a better result, and definitely you will get better result by your hard labor. So let's start our class. We were just trying to review our chapters, and sequentially the chapters is running is chapter 5, state of matter and pressure. And in this chapter we had discussion on different important topics, and we had just started practicing of creative type question. In my last class, I just tried to show an example of creative question, and in today's class I'll just continue with some other creative type question. As I have told earlier, the important portion or important content of this chapter related to creative type question are buoyancy related question, Pascal's law related question, density related question. We are just trying to solve some question related to this topic. We just had discussion about Pascal's law and question related to that topic. Today we will try to focus on some other topic. My first question is here related to buoyancy, or just related to Archimedes' law. As we have known about Archimedes' law, related to that law, just at first look at the stain. Question number 2. The area of the lower part of a rectangular block is 25 centimeter square. It is sunk into water. The height of the block is 2 centimeter. The container is 5 centimeter empty, and remaining part is filled up with water. That means if we just follow the diagram over here, rectangular block is just immersed into a container. The area of the block is 25 centimeters square. The height is 2 centimeter, and the container is 5 centimeter empty, and remaining part is filled with water. And from the diagram we also get some important that the height of the total container is 12 centimeter. The mass of the block is 200 gram, and weight in water is 1.47 Newton. Whenever you just get a mathematical type question or creative type question, first of all read out the stem just read out the stem for several times, so that every point gets clear to you, and you just can find out the necessary information from the stem that will help you to solve the other question. So first of all, try to repeat the stem again and again. Okay, what are the questions related to this thing? First of all, what is bulk modulus? Second question is, Young's modulus of elasticity of rubber is 0.9 Newton per meter square. What do you mean by this term? And question number C, find out the pressure at the lower surface of the block. And our question number D is, does it follow the Archimedes principle? So first question is, what is bulk modulus? We have known about bulk modulus in our previous lecture. What is bulk modulus? Bulk modulus is termed as the proportion of volumetric stress related to the volumetric strain of a material. Bulk modulus is specially related to volume of a material, and in a word, the ratio of volumetric stress to volumetric strain is called bulk modulus. Okay. Question number B, Young's modulus of elasticity of rubber is 0.9 Newton per meter square. What does this line just what we can mean by this line? Young modulus is specially related to lengthwise tension or compression, as we have learned in our in this chapter that Young modulus, this is totally related to length. So Young modulus of elasticity of a rubber is 0.9 Newton per meter square. We can explain in two ways. First of all, I can say that for changing 1 meter length, the rubber requires 0.9 Pascal pressure. Just from the line of 0.9 Newton per meter square, from this line we can say for changing 1 meter length, the rubber requires 0.9 Pascal or 0.9 Newton per meter square pressure. But from the equation of Young modulus, we can explain in another way. Just have a look on the equation of Young modulus. On the first class of review, we just had discussion on Young modulus and its equation. I think you can recall that one, that what was Young modulus? Y equals f L naught divided by A into L minus L naught. What was F was our applied force, or F by A is stress here. L naught was the object's initial length, and L is the change in length. So from the equation of Young modulus, we can write it another way: F L naught divided by A into del L, where del L just denotes the total change in length. So in this equation, if we just apply A equals 1, or if we just imagine that A equals 1 meter square and del L is equals L naught, del L equals L naught means the change in length will be exactly equal to the initial length. Then from the equation we can say Y equals F, and by observing this assumption, we just can express the Young modulus as for unit cross-sectional area, as we have just written that A equals 1 meter square. That means for unit cross-sectional area, by applying 0.9 Newton force, the change of length will be exactly equal to the initial length. That means Young modulus of rubber is 0.9 Newton per meter square. We can explain this line by this way also, and according to our equation, I think this is the better one for the explanation of Young modulus. So we have just explained the question number B. Now question number C. What was our question number C? Question number C was, find out the pressure at the lower surface of the block. find out the pressure at the lower surface of the block, we just know the equation of pressure. P equals H rho G, where H is the depth beneath the block, as the block is immersed into the water of the container. So H is depth beneath the block. And so what will be the depth beneath the block? If we just follow the diagram again, look at here on this diagram. The blocks over the overall height of the container was 12 centimeter, and the empty portion of this container was 5 centimeter. So if we just minus this term, then we will just get the overall height of the block. That means by overall height of the block is 2 centimeter, but the depth beneath the block will be 7 centimeter from our calculation, or from our diagram. Then total pressure will be H rho G, as the block is immersed in water, so its density will be definitely 1000 kg per meter cube. And as we know, the value of gravitational acceleration, that is 9.8. Putting these values on this equation of P equals H rho G, we just get the overall result here will be 686 Pascal. Okay, this was our third question, that what is the find out the pressure at the lower surface of the block. This is our desired result of pressure at the lower surface of the block. Okay, we can just determine this height in another way. We just can add two things here, the block's upper surface and block's height. For determining the height, we can just add two things here. That means depth from water surface to block's upper surface, that is 5 meter, and block's height is 2 centimeter. By adding those two things, we also get the depth beneath the block. We can here just use another description, that means 5 plus 2 centimeter. 5 plus 2 means for 5 meter is the depth of water surface to block's upper surface, and plus 2 meter is block's height. From that sense, we also get the depth beneath the block is 0.07 meter. Okay, so using these values, we just get the pressure P equals 686 Pascal. Question number D was, does it follow the Archimedes principle? As we know from Archimedes principle, if an object is just immersed in water, if the lost weight of that object is exactly equal to the amount of water displaced by the object, then we can say that the incident follows the Archimedes law. So at first we have to sort out the lost weight of the object. So let's just find out the lost weight of the object. What will be that? Block's weight in water is just mentioned in our question. Block's weight in water is 1.47 Newton, and block's weight on water on air, block's weight on air, that is from the equation W equals mg, we can write 0.2 into 9.8, and we just get the weight on air is 1.96 Newton. So the weight is not similar at air and water, so some weight are definitely lost here. So the lost weight in water will be W minus W prime, that means 0.49 Newton. As we have found the lost weight in water, now we have to find the weight of displaced water. What is the formula for that? Weight of displaced water is v rho g. From this equation, from this formula, we just get the weight of displaced water. That is also a equation for buoyancy. From these we just get the weight of displaced water is 0.49 Newton, where A equals 25 centimeter square. We'll just convert into SI unit, meter square, and H, that means the height of the object was 2 centimeter. These will be converted on meter, 0.02 meter, and putting other values we just get the weight of displaced water is also 0.49 Newton. As we are getting from our calculation, the lost weight of the object in water is just exactly equal to the weight of displaced water by the object. Then we can say the incident follow Archimedes law. Okay, this is a question related to Archimedes law, and I think you have understood the procedures over here. At first I have said earlier that at first you just try to focus on whatever you have to determine, and what are the information, what are the logics behind that. If we can just determine that one, the procedure will get clear to us. Okay, so we have seen our first example. I just want to discuss another example here. The first of all, just let's see the stain of our third example, and the second one of today's class. Question number 3. If the objects P and Q, here on the diagram, two objects P and Q are just mentioned. P and Q are kept separately at the water filled container of R, then it is seen different value of buoyancy. Here the informations are related to diagram. That means this is for example, this is a cube that is mentioned as P, and this is a sphere that is mentioned as or named as Q. What are the informations over here? The length of P is 3 centimeter. Length of P is 3 centimeter. The weight or the mass of P is 54 gram, and it is a cube. And this is a sphere named as Q. Its radius is 2 centimeter. Its mass is 54 gram, and this is a water filled container named as R. So if the objects P and Q are separately immersed on container R, then it is seen that the buoyancy will be different. So according to this theme, what are the question? Our first question is, what is buoyancy? Second one is, why does rotten egg float on water? Third one is, determine the density of the object P. And last question is, what is the reason of difference of buoyancy of the objects P and Q, though they have the same mass? As from the diagram, we just find it that the mass are same for both objects, that is 54 gram, but it is also mentioned in our stain the buoyancy is different. So what are the reason behind this? We have to find out. Question number A, what is buoyancy? We have already known about buoyancy. It is an upward force whenever an object just immersed into a fluid. Fluid means this can be a gas form or the liquid form. Liquid and gas both are termed as fluid. Whenever we just say fluid, that means this is true for liquid and for gas also. So whenever an object is immersed in fluid, that feels an upward force, and that force is called buoyancy. So this question, overall question, is related to buoyancy. Number B, why does rotten egg float on water? Actually, we just see eggshell is a solid part, but it is actually shell of different pores. So rotten egg floats on water because its density is less than water. Whenever an object floats on water, that means the density of that object is less than the density of water. The things are different for rotten egg and fresh egg, because whenever we just immerse in fresh egg into water, the eggs just sink into water, but a rotten egg floats on water because of having more density than water. Pure egg or fresh egg immerses in water, but as the egg ages, then air enters the egg and the air cell becomes larger. Air enters the egg, so that the porous side of, or porous shell of the egg becomes more larger, and these acts as a buoyancy aid. When egg becomes rotten, fluid evaporates. As the egg ages, the pores of the shell become more larger, so the fluid from the inner side of the egg evaporates through the porous cell, and then oxygen and other gases just gets into the egg. So as gas enters into the egg, for a same volume, the density of egg becomes less. That is the main cause here why just rotten egg float on water. Question number C, determine the density of the object P. Determine the density of the object P. We have to determine the density. We just know the familiar equation of density, rho equals m by v. Here what are the informations for P? That means for cube, the mass is 54 gram, that means 0.054 kg. The length is 3 centimeter, that means 0.03 meter. So the volume, as this is a cube, so the equation for volume is L cube, and we just get the value here, 2.7 into 10 inverse 5 meter cube. So the density, rho equals m divided by v. Following this equation, we just get the density is 20,000 kg per meter cube. This was our question number C. And question number D, though the both object has same mass, but the buoyancy is different. What is the logic behind that? First of all, we have to measure the buoyancy for both the objects. For object P, we have found the volume Vp is equals 20,000 kg per meter cube. At the same way, we have to determine the volume of sphere V cubed. As this is a sphere, for this we can use the equation 4 by 3 pi r cube, and the radius is given in our question. R equals 2 centimeter. Converting into meter becomes 0.02 meter. So by following this rule, 4 by 3 pi r cube, we just get the volume of sphere is 3.35 into 10 inverse 5 meter cube. So we have found the volume of the sphere and the cube. Now for cube P, upward force or buoyancy in container R will be Fp, and we just know the equation for buoyancy is B rho g. Then for QP, the buoyancy or upward force will be, after our calculation, it will be 0.2646 Newton. And for sphere Q, the buoyancy will be, we will just get the buoyancy using the same law V rho g. Here for sphere Q, VQ rho g, and putting the values over here, we just get the buoyancy FQ is 0.3283 Newton. So from our calculation we just get this, the buoyancy for sphere q is more than the buoyancy of cube fp. So what was our question? Our question was, though the mass is same, but buoyancy is different. What is the logic behind this? So from our equation of buoyancy we just find that, what is the equation? F equals v rho g. That means the buoyancy is clearly depends on the volume, not on the mass. As the volumes of p and q are different, so in spite of having same mass, the buoyancy is different here. This was a question related to buoyancy. I think by practicing this type of question, overall question pattern on this chapter will be totally clear to you, and the more you will practice mathematical or creative type question, the more you will be self-confident, and the more you will be get ready for your any kind of exam, for in-house exam or for board exam. So boys, try to keep studying, try to keep learning, because spending time for learning is not wasting your time. Definitely you are utilizing your time for your better future, for your self-establishment. So be careful, just take care of your health, take care of your parents, and just pray for all, pray for yourself, pray for your institution, pray for your teacher. That's all for today. And just I want to give thanks to all of you for following my class. Thanks to all.